All right, welcome to this explainer. Today, we're taking a really fun thermal journey up and down the thermometer to explore the totally fascinating world of water's phase transitions. We're going to unlock the invisible physics that govern everything from the ice in your glass to the clouds in the sky. And trust me, it's pretty mind-blowing once you see how it all connects.
So, here is our roadmap for today's scientific adventure. Melting and solidification, boiling and vapor pressure, evaporation versus boiling, condensation and air humidity, and finally, the water volume freezing anomaly. It's a packed journey, so let's jump right in.
Starting with Section 1, melting and solidification. Let's drop right to the bottom of the thermometer.
So, what exactly is fusion? Well, it's simply the passage of matter from a solid state right into a liquid state. And it's not just about ice cubes, you know? This exact same principle is what allows heavy industry to melt down rigid substances, like metal, and remold them into everyday items, like the actual license plates on our cars.
Now, check this out. If you place a thermometer into a beaker of melting ice, you'd probably expect the temperature to gradually climb as it melts, right? But it doesn't. The rule here is that the temperature stays perfectly constant at exactly 0 degrees Celsius. It literally will not budge until every last piece of that ice has completely melted.
And the exact inverse is completely true for solidification. Water turns back into solid ice at that exact same 0-degree mark. In fact, if you plunge a test tube of water into a super chilled mixture of crushed ice and salt sitting way down at -15 degrees, the water inside that tube will still pause and solidify at exactly 0 degrees. 0 is kind of this magic gateway between the two states.
Okay, so phase changes happen at specific thermal milestones. But what if we really turn up the heat? What happens to these rules when we blast that water with heat until it fiercely bubbles?
Which brings us to Section 2, boiling and vapor pressure.
We define boiling very specifically. It's matter passing from a liquid to a gaseous state, but, and this is absolutely crucial, it happens inside the liquid itself. It's when those large bubbles form deep down and rise to violently burst on the surface. And just like melting ice, this only happens at a definite, constant temperature.
But there's a really cool caveat here. Imagine you're boiling water in a flask, but you trap the escaping vapor with a cork. The pressure inside that flask is going to start to rise. And as that vapor pressure increases, it physically presses down on the liquid. It's literally making it harder for the water to turn into a gas. Because of this, the boiling point of the water actually increases. You have to pump in even more heat to get it to boil. So yeah, pressure changes everything.
But wait, hang on. This presents us with an everyday mystery. If a liquid absolutely needs to reach a high, definite boiling temperature to become a gas, how on earth do wet clothes get dry out on a clothesline? I mean, your backyard certainly isn't boiling.
To solve this one, we have to look at Section 3, the massive difference between evaporation and boiling. Here's where the physics gets incredibly elegant. Boiling, as we just learned, happens strictly inside the liquid at a definite temperature. But evaporation? That is strictly a surface-level phenomenon, and amazingly, it can happen at any temperature. It's simply the liquid molecules right at the exposed surface slowly sneaking away into the air. This is the exact invisible force pulling water vapor up from a cold sea to form clouds, and it's what dries your laundry in the breeze.
Because what goes up must come down, let's cool things off for Section 4, condensation and air humidity.
You've definitely seen this happen. Leave a really cold bottle of water out on a warm table, and within minutes, the outside is covered in sweating droplets. But think about it, where does that water actually come from? It's not magically leaking through the plastic. Those droplets are actual physical proof that you are surrounded by invisible water vapor right now. We call it humidity. When that warm, invisible vapor hits the freezing cold surface of your bottle, it rapidly loses heat and undergoes condensation. The cold surface essentially forces the gas to turn back into a liquid right before your eyes.
All right, we are dropping all the way back down the thermometer for our final and, frankly, explosive stop, the water volume freezing anomaly. Let's think about candle wax for a second. When liquid wax cools down and solidifies, the center actually sinks inward. It does this because, like almost everything else in the universe, it loses volume and shrinks when it freezes. So, does water shrink or expand when it turns to ice? Well, just look at a shattered glass bottle left in the freezer. Water completely breaks the rules.
It does the exact opposite of most substances. Its volume powerfully increases when it solidifies. When water molecules freeze, they lock into a crystalline structure that takes up more space than when they were freely moving as a liquid. And this expansion is so incredibly strong, it will easily burst a sealed glass bottle from the inside out. No way around it.
To wrap up our explainer today, let's quickly review the fundamental rules we've covered. 1. Temperature stubbornly stays the same during a state transition. Remember, the ice melting right at 0. 2. Vapor pressure elevates boiling points. And 3. Volume drastically changes when states change, with water being the ultimate rule breaker.
So, now that we've taken this thermal journey together, take a look around your kitchen today. You're constantly surrounded by these processes. Next time you see a sweating bottle or a boiling pot, which invisible physics rule are you going to notice first? And hey, if water breaks the rules here on Earth, what other bizarre physics anomalies are hiding out there in the universe? Something to think about. Keep questioning, and I'll see you in the next explainer.